All right, we're going to be looking at our last page of thermochemistry notes. Enthalpy, which is any of your delta H, or H values. So again, delta H is change in energy. So whether it's formation, reaction, combustion, those are all what are called state functions. That means it doesn't matter how the reaction takes place, only the overall change. So there can be numerous steps. So think of it as doing algebra in two different ways, but coming up with the same answer. Whether you do substitution or elimination, they both should give you the correct answer in a systems of equation type problem. So this is really applicable to what's called Hess's law of heat summation. The enthalpy change of an overall process is the sum of the enthalpy changes of its individual steps. So we are going to be looking at calculating the standard enthalpy of formation, or the delta HF value for acetylene C2H2 from its elements. So first thing you kind of have to know is this is your target. So when we're done, this is what we need to end up with. So the values that we know are the heat of formation of CO2. So you'll see CO2 being produced from its elements. You're going to see the same for water being produced from its elements. Notice the phase notations. Okay. And the heat of formation, and we also have the heat of combustion. So we know how much energy acetylene gives off when it burns. So we have these three equations. So we need to work through the process to rearrange and cancel the parts of this equation until we get our target. So first thing I'm going to do is I need C2H2 as a product, so we're going to reverse reaction C, which changes the sign of delta H. Oxygen, CO2, and water do not appear in our original target equation again, so we just have graphite and water in our target equation. Sorry, I'm messing around with formatting here. So again, no CO2 or water in our target equation. So the first thing I do is rearrange this. So I'm just taking this equation and flipping it. So 4CO2, 2H2O, 2C2H2, 5O2. And since I'm switching it, it now becomes endothermic instead of exothermic, so I'm changing the sign. Since 4 CO2 molecules are present in this equation, I have to multiply my equation A by 4. So you'll see, oh, I did miss a bracket here. I'm distributing this 4 the whole way. So 4 carbon graphites, 4 diatomic oxygens, and 4 CO2 molecules. And then what I do to the equation, I have to do to the delta H value. So 4 times the negative 393.5. Okay. So I'm going to highlight these equations so it kind of helps us for down the road. If you want to do this, it might be helpful if you have a printout of this to do for your notes as well. So we have 2 water molecules present, so I have to do the same thing to my water equation. So I'm going to multiply that through by 2. And again, same thing, distribute that 2, so 2 times 1 is 2, 2 times a half is 1, 2 times 1 is 2, and then 2 times my delta H value. And again, I'm going to highlight that one because that's the completed one. Okay, so in the next section, you'll see that I've taken the 3 highlighted equations and combined them into this here, and then I'm going to show you with some highlighting also how to cancel out. So my CO2s are going to cancel. Okay, so what I have as a reactant, what is a product, has to cancel. My 2 H2Os liquid are going to cancel. Okay, and then my 5 O2s, you'll have to be careful. So they're here. 4 plus 1 is 5, and 5 here. So those are going to cancel out. And what I'm left with then are simply the things that I want to form acetylene. So 4 Carbon graphites, 2 hydrogen molecules, and 2 acetylenes. Now, if you remember back, our target equation was just one of these, so I'm dividing both of these by 2, which means I have to divide this by 2, which gives me my final equation of 2 graphites, 2 hydrogen molecules, 1 acetylene molecule, which gives me a heat of formation of 226.6 kilojoules for that reaction. And that is Hess's law.